Scientists create computer simulations of the early universe, using sophisticated mathematical models and computational algorithms to mimic the conditions and processes that occurred in the moments after the Big Bang. These simulations are critical to understanding the complex dynamics of cosmic evolution, because they allow researchers to visualize and analyze phenomena that cannot be observed directly. The process begins in theoretical physics, where scientists develop models based on established theories in cosmology and particle physics. The equations governing these models take into account a wide range of factors, including the behavior of matter and energy, the effects of gravity as described by the general theory of relativity, and quantum mechanics, especially in the extreme conditions of the early universe. Researchers often use numerical methods to solve these complex equations because analytical solutions are generally not available for the high-energy, high-density scenarios present in the early universe. Once the equations are formulated, scientists use powerful supercomputers to run simulations that trace the evolution of unformed matter, radiation, and the very fabric of space-time itself. These simulations can model various scenarios such as cosmic inflation, the formation of primordial fluctuations, and the subsequent evolution of large-scale structures. Varying initial conditions and colliding them with observational data help refine the models, contributing to a deeper understanding of how various factors influenced cosmic evolution. In addition to cosmological simulations, scientists can also model particle interactions in high-energy environments like those in the early universe. These particle physics simulations explore the behavior of fundamental particles under extreme conditions, shedding light on the forces that governed the formation of matter as the universe cooled. The results of these computer simulations allow us to understand the fundamental dynamics of the early universe and learn how galaxies formed, how the cosmic background radiation evolved, and how the geometry and structure of the universe evolved over time. By comparing simulation results with actual telescope observations and space measurements, scientists can validate their models, leading to a more complete understanding of the fundamental processes that have shaped the cosmos. Through a combination of theoretical and computational methods, researchers continue to push the boundaries of knowledge about the origin and evolution of our universe. N-body modeling is a powerful computational tool used in astrophysics and cosmology to study the dynamics of systems composed of many gravitationally interacting bodies such as galaxies, stars, and dark matter. The term N-body refers to the number of particles or objects being simulated, where N can represent any number, from a few to millions or even billions. These simulations allow scientists to analyze complex gravitational interactions and how structures evolve over cosmic time. In the context of cosmic structure formation, N-body simulations help researchers model the behavior of matter in the universe, particularly dark matter, which accounts for about 24% of the total mass energy. By representing each particle in the simulation as a small element of dark matter, physicists can trace how these particles come together over time due to gravitational attraction. This process is important for understanding how galaxies form and evolve. How these gravitational structures grow results in the diverse cosmic tapestry we see today. The simulations start with an initial particle distribution that reflects the conditions of the early universe. Researchers typically use a cosmological model based on the standard model of cosmology, which includes parameters such as matter density, dark energy, and curvature of space. By running the simulation for billions of years of cosmic time, scientists can observe how initial fluctuations in matter density evolve into larger structures such as galaxy clusters and superclusters. N-body simulations provide valuable insights into a variety of cosmic phenomena, including the formation of the cosmic web, which describes the large-scale structure of the universe, consisting of strands of galaxies and vast voids. They also help scientists understand phenomena such as gravitational lensing, the behavior of galaxies and clusters, and the dynamics of galaxy mergers. Comparing the modeling results with actual telescope observations and surveys allows researchers to refine their models, expanding our understanding of the nature of dark matter and the processes underlying cosmic evolution. By elucidating the mechanisms of structure formation, N-body modeling contributes significantly to our overall understanding of the universe, guides future research, and shapes theories about its past, present, and future. Cosmological models account for dark matter and dark energy, fitting these mysterious components into the overall picture of the composition and dynamics of the universe. Dark matter and dark energy play a crucial role in understanding the structure, behavior, and evolution of the universe, yet remain virtually invisible and undetectable by conventional means. Dark matter makes up about 24% of the total mass energy of the universe. Cosmological models treat dark matter as a non-baryonic substance that interacts primarily through gravity, affecting the motion of galaxies and the large-scale structure of the cosmos. To incorporate dark matter into these models, scientists investigate its gravitational effects on visible matter. For example, they observe the rotation curves of galaxies and the motion of galaxies within clusters, finding that the observed gravitational attraction cannot be explained by apparent mass alone. This discrepancy leads to the conclusion that there must be additional mass, discovered through gravitational effects rather than direct observation. To accurately reflect the role of dark matter in the structure of the universe, cosmological models often use N-body simulations that mimic the gravitational interaction of huge amounts of dark matter along with ordinary baryonic matter. In addition, the prevailing cosmological model is the dark matter model known as the lambda cold dark matter model, which includes dark energy represented by the lambda cosmological constant. This model explains the observed acceleration of the expansion of the universe by attributing it to the repulsive force of dark energy. Dark energy accounts for about 72% of the total mass and energy density. Although its exact nature is still debated, it is widely regarded in cosmological models as a smooth and homogeneous component of energy that permeates space, exerting negative pressure, resulting in accelerated cosmic expansion. By including dark energy in cosmological equations, scientists can explain the relationship between the expansion rate of the universe and its mass-energy content, leading to successful predictions that are consistent with observations of supernovae and the cosmic microwave background radiation. Together, dark matter and dark energy provide a more complete picture of the composition and behavior of the universe. By reflecting their gravitational and dynamical effects in cosmological models, researchers can better understand how the universe has evolved since the Big Bang, as well as its ultimate fate in the distant future. These concepts illuminate the significant role that these elusive components play in shaping our universe. The lambda cold dark matter model is the dominant cosmological scheme that describes the large-scale structure and evolution of the universe. This model includes two key components: the cosmological constant, denoted by the lambda, and cold dark matter, a form of matter that interacts only through gravity and is thought to account for a significant fraction of the mass of the universe. The lambda cold dark matter model has taken center stage in our understanding of cosmology because of its ability to explain a wide range of observational data. At its core, the lambda cold dark matter model explains the expansion of the universe by the interaction between dark energy, represented by the cosmological constant, and the dynamics of matter, both visible and dark. The cosmological constant is related to dark energy, which has been found to be the source of the accelerated expansion of the universe observed in distant supernovae and the cosmic microwave background radiation. According to this model, dark energy is a homogeneous energy density distributed throughout space and exerts a negative pressure that affects the rate of cosmic expansion. Cold dark matter is a form of matter that travels slowly compared to the speed of light, allowing it to shrink under its own gravity. Unlike hot dark matter, which moves at relativistic velocities and does not allow structures to form efficiently. In the lambda cold dark matter model, cold dark matter plays a crucial role in the formation of structures. Initially, small density fluctuations laid down by quantum processes in the early universe grew over time due to gravitational attraction, leading to the formation of galaxies, clusters, and the vast cosmic web we see today. The lambda cold dark matter model provides a consistent framework for understanding several key phenomena, including the flat geometry of the universe and the observed distribution of galaxies. It also accurately predicts temperature fluctuations found in the cosmic microwave background radiation, which is strong evidence for its validity. In addition, the model allows scientists to infer the relative contributions of dark energy, dark matter, and baryonic, or ordinary, matter to the formation of the current composition of the universe. Overall, the lambda cold dark matter model offers a comprehensive and consistent description of the evolution of the universe, explaining both large-scale structure and accelerated expansion. By reconciling theoretical predictions with observational data, the model remains a fundamental cornerstone in the field of cosmology, guiding ongoing research into the mysteries of the universe and its constituents. Scientists use supercomputers to model the first moments after the Big Bang, simulating the extreme conditions that existed at the time. The universe was originally incredibly hot and dense, a state that is difficult to replicate in a laboratory setting. Using supercomputers, researchers can recreate these conditions through sophisticated algorithms and simulations, studying how matter and energy behaved when the universe first began to form. During the modeling process, these powerful machines perform equations of state that determine how different particles interact at such extreme temperatures and densities. With it, scientists can investigate the formation of fundamental particles such as quarks and electrons, as well as the creation of protons and neutrons. The sophisticated models can also illustrate a period of rapid expansion known as cosmic inflation, allowing researchers to hypothesize how the universe went from this hot, dense state to the cooler, more structured cosmos we see today. In addition, these supercomputers utilize huge amounts of data from particle physics experiments, such as those at the Large Hadron Collider. By integrating this data with simulations, scientists can test their models against real-world observations. This process not only deepens our understanding of the early universe, but also provides insight into the fundamental physical laws and forces that shape our reality. The results of these computer models can lead to predictions about the evolution of the universe, influencing our knowledge on topics such as the cosmic microwave background radiation, galaxy formation, and dark matter. As technology advances, modeling becomes more sophisticated, allowing scientists to look deeper into the moments immediately following the Big Bang to the origins of everything we know. Current cosmological simulations, despite their impressive capabilities, face a number of significant limitations. One of the main challenges is the complex nature of the forces and particles involved in the evolution of the universe. While simulations can effectively model large-scale structure and behavior, they often fail to accurately represent the complexity of galaxy formation and interactions on smaller scales. This discrepancy can lead to a gap between simulation results and real observational data, especially with respect to the distribution and behavior of dark matter. Another limitation comes from the enormous computing power required for detailed modeling. Even with supercomputers, there are limitations on the resolution and size of the simulated volume. Most simulations can either achieve high resolution in a limited region or cover a large region at lower resolution. This trade-off means that some important phenomena, such as star formation or black hole dynamics, cannot be fully accounted for. Thus, little is known about how these processes affect global evolution. Moreover, our current understanding of fundamental physics and planetary parameters is incomplete. For example, the enigmatic nature of dark energy and dark matter is a real constraint. Most simulations are based on simple models or assumptions about these complex components. If their properties are not fully understood, model predictions may be unclear or incorrect. Finally, the human factor also plays a role. Many simulations involve a selection of initial conditions, model parameters, and simplifications made by researchers. Different teams may have different ideas and produce different results. Improving the accuracy of planetary modeling requires researchers to work together and continually improve observational and theoretical physics techniques. Scientists test and refine their cosmological models through a systematic process that involves comparing model predictions with actual observations. They analyze data collected by telescopes, both ground-based and space-based, that acquire images and spectral information from distant galaxies, the cosmic microwave background radiation, and other astronomical phenomena. This empirical data serves as a critical benchmark against which theoretical models are tested, allowing scientists to determine how well their simulations reflect what is actually observed in the universe. Researchers also practice peer review and collaborative research. They share their results with the global scientific community, receiving feedback that may reveal potential flaws in assumptions or methodologies. Collaboration with different researchers allows the integration of knowledge from different fields, which improves the accuracy and completeness of the model. Researchers often publish their results in scientific journals, where they are scrutinized, contributing to an atmosphere of constant refinement of cosmological theories. Refinement also occurs through iterative modeling. When new data become available or when existing data are reanalyzed, scientists revise their models, adjusting parameters and recalibrating simulations to better fit the updated information. For example, improved measurements of galaxy distributions, cosmic expansion rates, or dark matter properties allow researchers to adjust their models accordingly. These changes can significantly improve the accuracy of predictions about the behavior of the universe. In addition, scientists use machine learning and artificial intelligence technologies in the modeling process. By training algorithms on huge datasets, researchers can uncover patterns and correlations that may be missed by traditional methods. This innovative approach can lead to the discovery of new relationships or the identification of previously unknown phenomena, ultimately enriching our understanding of the cosmos and leading to better theoretical frameworks. The interplay of empirical observations, collaborative efforts, and technological advances makes the validation and refinement of cosmological models an evolving and dynamic process. Artificial intelligence is playing an increasingly important role in both creating and analyzing cosmological simulations, changing the way scientists think about the universe. This is one of the most important applications of data analytics. The amount of data coming from astronomical observations and planetary modeling can be overwhelming. Machine learning algorithms are very good at processing large amounts of data, identifying patterns and making connections that are difficult for humans to understand. For example, artificial intelligence can classify galaxies, analyze their shape, and predict their composition based on features extracted from the data. When creating a simulation, AI can optimize model parameters in real time. Algorithms can learn different configurations and dynamically adjust them, leading to more efficient modeling. This approach allows researchers to explore a wider range of potential scenarios and outcomes in much less time than traditional methods. By harnessing the power of AI, researchers not only save time, AI also improves the accuracy and detail of models, making them more representative of the true physics behind the process. In addition, artificial intelligence can help in interpreting the results of cosmological simulations. They can help identify relationships between different cosmological parameters and assess the consistency of modeled data with observational data. Using techniques such as neural networks, scientists can develop predictive models that predict future astronomical phenomena based on current simulations. This synergy between AI and cosmology leads to a better understanding of complex systems and can help unravel the evolution of the universe and its fundamental components. Finally, AI facilitates collaboration by providing tools that improve visualization and communication between scientists. With sophisticated data visualization techniques using artificial intelligence, researchers can create interactive models and presentations that communicate complex ideas more clearly. The ability to convincingly illustrate results fosters greater collaboration between scientists and broadens the audience for cosmological research, making it more accessible to those outside the field. The integration of artificial intelligence into cosmological modeling marks a transformational shift in modern astrophysics, pushing research to new frontiers. Simulation serves as a powerful tool for scientists to predict the future of the universe by modeling complex physical processes and providing insight into how cosmic structures evolve over time. Using known laws of physics such as gravity and thermodynamics, researchers can create scenarios that show how different components of the universe interact and change. Such simulations allow scientists to explore different outcomes based on contrasting initial conditions and parameters, revealing potential paths for the universe. One important aspect is modeling cosmic evolution, which includes the formation of galaxies, stars, and other structures. By observing how these structures have behaved in the past, researchers can extrapolate patterns and behaviors to predict future conditions. For example, simulations can show galaxy mergers, changes in the rate of star formation, or the effects of dark matter on the dynamics of the universe over billions of years. These predictions help scientists understand not only the current state of the world, but also how it will evolve in the future. In addition, modeling can be used to study the effects of dark energy on the expansion of the universe. Because the world is moving so fast, it's important to understand how dark energy works. Researchers can manipulate different models of dark energy within simulations to explore different possibilities regarding its characteristics and effects over time. These studies lead to predictions about the ultimate fate of the universe, whether it will continue to expand indefinitely, reach a steady state, or eventually collapse. With these simulations, scientists also look at various cosmic events, such as supernovae or black hole interactions, which can have far-reaching consequences for the evolution of the universe. By analyzing how these phenomena evolve and their potential impact on surrounding matter and energy, researchers can refine their predictions. Thus, cosmological modeling not only deepens our understanding of historical events, but also allows scientists to make informed predictions about the future of the universe, thereby enriching our knowledge of the cosmos. Cosmological modeling has led to several surprising discoveries that have changed the way we view the universe. One significant discovery is the tangled structure of the cosmic web. Early simulations have revealed a vast network of galaxies connected by threads of dark matter and gas, which contradicts our intuitive ideas about how matter organizes itself on large scales. The discovery of the cosmic web has emphasized the importance of dark matter, which plays a crucial role in shaping the large-scale structure of the universe, despite being invisible and poorly understood. Another unexpected discovery from the modeling is the role of feedback processes in the formation of galaxies. It was originally thought that gas simply collapses to form galaxies, but modeling has shown that energetic events such as supernova explosions and active galactic nuclei significantly influence star formation. These feedback mechanisms can expel gas from galaxies, regulate the rate of star formation, and even trigger the formation of new stars. This complex interaction showed how dynamic and complex galaxy evolution is, and led scientists to rethink previous assumptions about galaxy formation. The simulations also challenged existing theories regarding dark energy. Initially, scientists assumed that the influence of dark energy would be relatively uniform throughout the universe. However, sophisticated models showed that the distribution of dark energy varies, leading to different regions of expansion velocity. This discovery raises fundamental questions about the nature of dark energy and its role in the end of the universe. As researchers' interests turn toward a deeper understanding of dark energy, these surprising modeling results are stimulating new lines of research. Finally, the model reveals the existence of rogue planets, planets that do not orbit a star, but instead move through the galaxy. This insight expands our understanding of planetary systems and their dynamics. The simulations showed that interactions between celestial bodies, including interstellar collisions, can push planets out into interstellar space. The discovery reveals the complexity of planetary interactions, opens the way for further research into the formation and habitability of planets, and suggests that our solar system may not exist according to previous ideas. These results demonstrate the power of planetary modeling in challenging hypotheses, and reveal the complex and fascinating nature of the universe.